So here we started to drift a little bit into abstract territory, so let's return to things which are simple and concrete. And for this we are going to look at some properties of expectation values. Namely at some very simple relations between different expectation values. And this is really just as simple as saying that if you have a wave function psi of x, which might look like this, and then you consider the wave function shifted in position. So if this was 0, we now refer everything to the position x0. Then the corresponding expectation value, which sort of gives you an idea of the average position, should just be shifted as well, namely by x0. And the only really interesting thing here is perhaps the sign, which we can immediately see from this graphical representation because we go from 0 to x0. But we can see this also mathematically by evaluating this expectation value simply with this wave function here. So this new wave function integrating over all space. And there I simply left some space to insert a minus x0 and a plus x0, so that we can split this into two integrals. One which looks like this, and another one where x0 is just multiplied by the wave functions here, which is just related to our normalization integral, because x0 is a constant, so we can pull it to the front. Now, because these are all integrals over all space, we can simply shift the integration variable. So wherever we have x minus x0, instead of integrating over x, we can just integrate over this variable here. So this one here is actually identical just to the expectation value of x evaluated in the unshifted wave function. And this normalization integral just becomes 1, and therefore we obtain plus x0, just as written here. This shift can be interpreted in different ways. For instance, it can really be the wave function of a particle sitting at different positions in space. But in the following, we're just going to exploit this to select our origin of our coordinate system in space, such that this expectation value simply vanishes. So with this fixed, we would then, for instance, ask questions about the second moment, the expectation value of x squared. And for instance, we can then ask what happens if instead of the wave function psi of x, we have the wave function psi of ax, where a is a scale factor. So if we start out with a wave function psi of x, which is centered at the origin, and we apply such a scale factor, assuming that this is, for instance, larger than 1, then the wave function would become sort of more confined to a smaller region in space. And this should clearly affect such expectation values. And indeed, we see that they'll simply become multiplied by a factor 1 over a squared. So this could be used to use some units of position so that this expectation value indeed becomes 1. Is it also possible to shift the expectation value in momentum? Well, this is indeed possible too, and is indeed very simple, because if we start out with a wave function psi of x and multiply it by a plane wave, where I just set this constant here to p0, to distinguish it from other p's that we encounter, And if this one corresponds to an expectation value of momentum p, then this will have an expectation value simply shifted by p naught. This again follows straight from our definitions when we calculate the expectation value of momentum with this new wave function. So we insert the complex conjugate of this here, and then we apply the momentum operator on this part here. Again, integrating over all space. Well, here we have this expression as always. So we calculate derivatives and apply the product rule. One derivative acting on x here and another one acting here. And the one acting here is very interesting because this is of course just the momentum eigenfunction. So here we will just obtain a factor p naught. And here we will just obtain the normal derivative here. So we get two terms. One where we apply the derivative here. Then this piece and this piece will just cancel. So we have basically just p times psi of x dx. And this is our original expectation value p. And another one where we now have just this value p naught. Again, the exponential functions cancel. P naught is again a constant, so we can once more pull it to the front and end up with our normalization integral, which is just 1. So all that we obtain is again just p naught. So this expression here. So this we could use to move into some kind of moving frame in which our expectation value for momentum then simply vanishes. So we can do some very simple transformations on our wave functions, and having exploited these freedoms, you could ask, can we then still do something for p squared? But then we see that we cannot do something for this expectation value because of the uncertainty principle. Because according to the uncertainty principle, the product of these uncertainties can never be less than h bar over 2. Well, choosing our origin so that the expectation value of x is equal to 0, and using units of position so that this expectation value is 1, as well as going into a moving frame so that this expectation value of momentum is equal to 0, we do have delta x equals to 1, and this is simply in some convenient dimensionless units, while delta p is then simply given as the square root of this expectation value here. So this means that we cannot choose this expectation value freely, simply because of this uncertainty principle here. In particular, using suitable units for position also fixes our units for momentum, simply because in quantum mechanics there is a mathematical relation between these observables. So whatever units we choose, for instance, we need to have this commutator here. But having some freedoms to select these expectation values in itself is already, of course, very useful. And indeed, it simplifies our discussion of the uncertainty principle. So we can use it to come up with a very compact proof. And for this, we are in particular exploiting that we can set these two expectation values to 0. With these choices of the expectation values, the squares of the uncertainties of position and momentum simply become these expectation values here. And now we can ask how small this product can become. And in order to do so, we first write down the definitions of these expectation values, both for x squared and for p squared. So in terms of these operators and these scalar products. And then we use the hermiticity of these operators to move just one of the two factors appearing in each instance here into the other entry of the scalar product. So this then looks just like given here. And now this suddenly looks like the absolute value squared of the length of certain states, namely the states that we obtained by multiplication by this operator or this operator here. Next, we are going to exploit a relation that you might be familiar with from vectors. Namely, when we multiply the squared length of two vectors, then this will always be larger than the square of the dot product between the two vectors. And these two expressions are indeed only the same when the two vectors are parallel to each other. And the same also applies to our complex versions of these dot products, our scalar products. And this inequality is then known as the Cauchy-Schwarz inequality. And this we are now going to exploit to say that what we have obtained is never smaller than this expression here. The absolute value squared of a certain scalar product. So this is a scalar product between this state and this state, which simply play the role of the vectors as given here. Now we are already very close to the end. There are basically only two steps. And the first one is to exploit some very simple features of complex numbers. The scalar product is such a complex number, and if you call it z, then the absolute value squared of z will be given by the square of the real part of z plus the square of the imaginary part of z. So these are squares of real numbers, so each of these two contributions is never negative. And therefore we can further estimate this by just using the imaginary part, so neglecting this part here. And this imaginary part we can simply write in terms of the scalar product by subtracting its complex conjugate. Now for the scalar product, this simply means to interchange the role of the two entries. So we obtain this expression here. And then, so this is the complex number minus its complex conjugate. We have to divide by 2i to get the imaginary part. And the square can then be just written like here. And now we are really very close, because next we are just going to use again that these are Hermitian operators. So we can move them again into the other position. So we have here xp, and then we have another term which is just px, and we can indeed combine these all already. So we get this expression here. So here we just have our commutator between the position and momentum operators, x and p, which is simply IH bar. And on top of this, this is just a constant, so we can pull this to the front. So what we obtain at this place is just IH bar psi psi divided by 2i absolute value squared. Well, this is our normalization condition, so we just obtain 1 and all the rest are just numbers. And taking the square of what is given, we just obtain h bar squared divided by 4. And this is indeed our final result, because this now gives us an estimate of the product of the uncertainties at the beginning. And Heisenberg's uncertainty principle now simply follows by taking the square root of both sides. This we can do straightforwardly because delta x and delta p are never negative. And so what we obtain is that the product of these uncertainties is never smaller than h bar over 2. So we have indeed recovered Heisenberg's uncertainty principle. And what is very nice about this proof is that it rests on our very general mathematical language and uses some very simple features instead of technical details, say of the Fourier transformation itself.